Rough seas can be a menace to a floating drilling vessel, especially during drilling operations. Rucker provides the solution to this motion problem, the drill string compensator. This program has been prepared to help you understand just what the Rucker drill string compensator is, what its major components are, how it works, and some of the basic operational procedure to follow when using it. You have been given a workbook that looks like this. Whenever we want you to use it, you will see this sign. Now turn to page 1 in the workbook. See the list of objectives? This is what we want you to understand from the program. Keep these objectives in mind as we continue so that you can more easily remember the information. At the end of the program, we will ask you to stop the playback unit and complete a quiz in the workbook. This is a self-check exercise to help you know if you fully understand the information. Now let's learn about the Rucker drill string compensator, or DSC for short. The DSC is a motion compensating system designed and developed to nullify the effects of drilling vessel heave on the drill string or other hook-supported equipment. Mounted between the hook and traveling block, the DSC is connected to deck-mounted air pressure vessels by a hose loop and standpipes. The system is controlled and monitored from the driller's control console. Weight on bit is determined by the tension setting of the DSC and the weight of the drill string. The bit weight is equal to the weight of the drill string minus the tension setting of the DSC. The DSC was designed and developed for full-time drilling operations bit weight control, for landing and retrieving the blowout preventer stack, for landing casing, well logging, coring, fishing, and suspending a motionless drill string on a BOP ramp. In other words, any operations requiring nullification of the effects of rig heave. From the console, the driller controls the DSC tension level and monitors its operation. While drilling ahead, the DSC controls the weight on bit. The driller incrementally lowers the traveling block to account for drill off and to maintain the compensator cylinders within its stroke capacity. The hook position indicator clearly depicts the position. The DSC automatically maintains the selected bit weight. The benefit of using the DSC is realized by completing a hole in fewer days on location. This results in being able to drill in high rig heave conditions, longer drill bit life, and being able to perform landing and retrieving operations faster or in higher heaves than without the DSC. Now that we've shown you the DSC in a working environment, let's take a closer look at the system components and how they work. We've already used some of the terms, but to help you better understand the system and remember the names of its components, we're going to group the parts into four main operational elements. As you become familiar with the system, you'll find that there are many ways to group the DSC components. But for this program, we'll list them as one, the main frame assembly, which contains the cylinders, rods, sheaves, chains, air oil reservoirs, lock bar subassembly, and the traveling block interface. Two, the hook frame assembly. Three, the air power supply, which consists of air pressure vessels, compressors, the hose loop, standpipes, manifolds, and piping. And four, the driller's control console, which contains the hook position indicator, valve controls, the weight indicator, and gauges. Let's go over that once more. The main frame assembly, the hook frame assembly, the air power supply, and the driller's control console. Here's how they function. The two compression-loaded hydraulic pneumatic cylinders on the main frame are supplied with high-pressure air. The air supply comes from deck-mounted air pressure vessels, or APVs for short. The APVs are connected to the DSC cylinders by the hose loop and standpipes. The tension level of the DSC is determined by the magnitude of the air pressure in the compensator cylinders. The pressure variation due to the expansion compression of air is determined by the volume of the air pressure vessels. The optimum volume normally selected is 6 275-gallon APVs. Different volume levels, however, can be installed. Power connection between the APVs and the DSC is by air rather than oil. This provides greater operational efficiency and eliminates operational shock. As the rig heaves upward, the DSC cylinder rods are retracted and the hook moves downward to maintain the selected loads. Actually, the hook remains fixed relative to the earth. The rig and compensator are what move, producing relative motion between the hook and the rig. The Kelly and drill string are also in motion relative to the rotary table. As the cylinder rods retract, the air flows from the cylinders through the hose loop and standpipes to the APVs. The friction loss of this flow is important because it directly affects the overall operational efficiency of the system, especially in high heave conditions. This is when the DSC is most needed and produces the most positive effects. The extended stroke design was developed to achieve a long compensating stroke with reduced vertical height. By use of the two-part chain system, 18 feet of compensation stroke is realized from only 9 feet of cylinder rod stroke. The short cylinders reduce the vertical mass derrick height required by the compensator. Reduced height also significantly reduces the dynamic cylinder loads imposed by pitch and roll of the rig. Reduction of cylinder motion, as related to rig motion, means that the rods travel only 1/2 as far as the rig does, thus reducing the piston packing wear to increase its life. Cable chain provides an efficient, flexible power linkage between each cylinder and the hook. This flexible linkage eliminates side loads from the cylinder rods, providing longer, trouble-free life. Because this link between the two cylinders and the hook frame is flexible, the need for cylinder synchronization is eliminated. The hook frame's guide dolly and the compensator's geometrical shape, which is an inverted triangle, provides coarse cylinder alignment. This eliminates interference between the DSC's moving and stationary parts. There are 6 chains supporting the hook frame. Each has individual length adjustments to ensure equal sharing of the load. The total strength of the chain is over 1,500,000 pounds. The chain can provide up to 6 years of life. Its replacement is determined by a simple length measurement which indicates chain bearing wear. There is no fatigue determination required, as in wire rope usage. The two air oil reservoirs supply oil to the rod ends of the compensator cylinders for safety control and lubrication. As the cylinder rods extend, oil flows from the rod ends through speed-limiting valves located here and into the reservoir. As the rods retract, air forces the oil back into the cylinders, keeping them well filled. The oil fully lubricates the rod and piston packings and the bearings to ensure maximum life. The speed limiting valve limits the extension speed of the cylinder rod if the drill string should break while the DSC is pressurized. Upon release of the load from the hook, the rods will begin to rapidly extend, forcing oil through the speed limiting valve. When the extension speed exceeds the maximum operational speed by about 15%, the valve closes down to limit the extension speed. It does this by causing hydraulic back pressure in the rod end. This inline valve responds instantly to prevent equipment or personnel damage. The cylinders are the main functioning components of the system. These pneumatic hydraulic cylinders operate as a compression-loaded unit and provide maximum uptime operation. The extension force is derived from high-pressure air on the piston of each rod. By use of the compression-loaded cylinder, only one set of packing is operated under high pressure. This means that internal friction is significantly less than if a tension-loaded cylinder had been used. Assembly of the cylinder permits easy field repair and parts replacement. Oil in the rod end of the cylinder provides lubrication to the rod packing and bearing and the piston packing and bearing. The cylinder's rod end cushion has a long stroke design to ensure safe deceleration in the event of free release while operating under load. The cylinder's blind end cushion eliminates mechanical shock that could be encountered when the traveling block is raised, putting full string weight on the hook. Each time the block is raised to lift the drill string from the slips or from the hole, the full drill string weight is landed on the hook. The blind end cushion provides a hydraulic cushion to produce a soft contact. The major functional design features provided in the cylinder are 1. Extra long bronze bearings which are located within the lubricating fluid. 2. A long stop tube to provide adequate distance between bearings. 3. Long hydraulic cushions on both rod end and blind end to prevent mechanical shock loading when stroked to stroke limit. 4. Hard chrome plated rod and cylinder barrel to provide hard wearing surfaces and corrosion protection. And 5. A packing system proved through years of service on Rucker's riser and guideline tensioners. The rod end sheave assembly is bolted to the cylinder piston rod. Its function is to translate cylinder force to the set of 3 chains on each side upon which the hook frame hangs. The principal elements of the sheave block include the sheaves, which are actually flanged rollers, tapered roller bearings, and a machine-welded frame. The hook frame is attached to the main frame and cylinders by the 6 chains. It uses the bail on the traveling block to carry the hook load from the main frame through the compensator onto the bail of the hook frame. The chain attachments, which are pivot points, are well above the pivot point of the hook bail. This load connection forms a stable inverted isosceles triangle rather than the inherent unstable right side up triangle with the load at the apex. The lock bar subassembly located in the main frame assembly mechanically locks the hook frame to the main frame and, in effect, the hook to the traveling block. The lock bar subassembly consists of the lock bar, a support spindle with bearings and springs, and an actuator cylinder. The hydraulic power for the actuator cylinder is supplied by the air-powered hydraulic power unit mounted in the driller's control console. Rucker supplies a new lock bar actuation system that eliminates the booster pump as the power source, replacing it with the pressurized air available in the console. The new system employs an air oil reservoir to supply the hydraulic fluid to the lock bar actuation cylinder. Pneumatic pressure is tapped from the high-pressure compensator supply and run from the control console to the reservoir mounted on the DSC. Actuator position is selected manually using the existing valve V1 lock bar on the control console with lock bar status indicated as before. The driller's control console is located adjacent to the driller's station. This permits easy performance of control functions and monitoring of all operations. Monitoring functions include the compensator stroke position, standby APV pressure, compensator hook load, position of the lock bar, and air oil reservoir pressure. Control functions at the console include compensator hook load adjustment, air compressor air dryer start-stop, lock bar operation, and air oil reservoir pressure adjustment. The hook position indicator provides the driller with an exact display of the hook position relative to the compensator's stroke capacity. It is large enough to be easily readable at a distance. The hose bundle is looped from the DSC to the standpipe valve assembly. There are 4 2-inch spiral wire wrapped air hoses rated at 3,000 psi which provide main pressure flow to the cylinders. 2 1/2-inch hoses are provided for lock bar operation. 1 1/2-inch hose provides the air oil reservoir pressure. An air safety valve is mounted at each end of the 2-inch air hoses. These valves automatically and instantly close in the event of a hose failure. This prevents loss of air and permits the intact hoses to continue normal operation. A stainless steel restraining cable is fitted inside each of the 2-inch air hoses to prevent loose end movements in case of a hose rupture. Standpipe valve assemblies are mounted atop each standpipe. The valve assemblies contain manual air hose shutoffs and a safety shutoff valve. The manual air valves are used for shutdown of a particular hose. Other valves identical to these valves are located on the compensator for isolating a defective hose from the DSC cylinders. In case of a hose breakage, the safety shutoff valve